Imagine a future where our entire civilization is powered by solar. What would such a future look like, and how far away is it really? To explore this question, let's look at some real-world examples. One of the first places we see the applications of solar energy, specifically photovoltaic solar panels, is in infrastructure. On residential, commercial and industrial buildings, especially those that are in remote locations and do not have access to the grid. Any such building or house can be equipped with first an inverter, which can stream the data from the solar system to the cloud, and second, with a battery, enabling the storage of any excess energy generated by the sun at daily hours so it can be used when the sun is out at night hours. And thanks to Stanford engineers, we might now also have the ability to generate electricity at night by supplying the panels with a thermoelectric generator, a device that generates currents through temperature differences. A homeowner who possesses such a system may also have the ability to charge his or her electric vehicle, reducing the need for charging stations. Now, if we consider a case where independent producers of solar power do have access to the grid, but not all of them have the capacity to store the extra energy, those producers might be able to trade this energy over the grid through a blockchain network. Many companies like WePower, SolarCoin, SunExchange or PowerLedger are implementing this type of distributed power and microgrid technologies in countries such as Estonia, South Africa, the US and Australia, just to name a few. Other companies and organizations are choosing to focus on the actual production and efficiency of solar panels. For example, using 3D printing methods to manufacture solar cells, or using a genetically engineered M13 virus to boost the efficiency of those cells. In the last few years, we have also seen the rise of perovskite as an alternative or additional material to the traditionally used silicon. Perovskite is a calcium titanium oxide mineral composed of calcium titanate. Pioneering work has been done by Oxford Photovoltaics and others in the development of low-cost perovskite silicon tandem cells. These are multi-junction cells consisting of both a silicon and a perovskite layer, and they allow you to absorb a wider range of wavelengths from the incoming sunlight. Tandem cells have the potential to achieve conversion efficiencies of around 38%. Compare this with the maximum theoretical conversion efficiency of silicon alone, which is about 29%. Research is still going, and more data is needed, especially on the durability of the material. However, perovskite seems very promising. In July 4th, 2006, Peter and Lyndon Reeve, two of Elon Musk's cousins, founded the company SolarCity. In 2016, Elon's company Tesla acquired SolarCity for $2.6 billion and reorganized it into its subsidiary Tesla Energy. This same year, they unveiled one of their main products, the solar roof. The solar roof is an attempt to seamlessly integrate solar generation into the roof of a building without relying on those traditional bluish solar panels that people usually use. The solar roof aims to be stylish while at the same time providing all the energy you need to power your home or EV. Besides Tesla, there are other companies whose aim is also the seamless integration of solar. For example, there's the German-based company Haliatech, who is developing transparent solar panels to be used for windows of buildings, cars, or whatever else tickles your fancy. There is the exotic Diaqua, who is masking solar panels as building materials to make them better fit with more traditional architectures. There are the soft and rolling solar panels produced by a company named PowerFume Solar. These require almost zero installation time, if you decide to install them. If you don't, they can be brought easily to any location and serve to provide up to 60 watts of power for a weight of less than 2 kilograms. As easy and simple to use as these sound, there's probably an even simpler way. Enter Solarpaint. Originally commercialized in 1994 by Diaso, an Australian solar company, this product is exactly what it sounds like. A photovoltaic paint that you lay on any surface and hook it to a circuit. The surface will generate an electrical current. More recent iterations of the form make use of perovskite to facilitate the reaction between the absorbed sunlight and absorbed moisture from the air to produce hydrogen fuel. Quite like photosynthesis. Next, I want to touch on solar farms. Besides the fully distributed perspective, there is great benefit of large solar farms spread around the globe. These can be on ground, a field or a desert, or on water, the so-called floating farms. Currently, the largest solar farms are on average between 13 and 31 square kilometers and generate between 600 and 1600 megawatts of power. To get a sense of scale, in order to power the entire US, we would need about 10,000 square kilometers of surface area to cover with solar panels. This might sound far off from our current capabilities, but consider that the US's surface area is approximately 10 million square kilometers, and in this light we need only 0.1% of it to power the whole country. A small portion of this would also be devoted to large grid-scale energy storage. It also turns out that agricultural land is the most suitable for solar farms in terms of efficiency. The most profit/power can be generated by the solar industry by replacing farmland with fields of solar panels as opposed to using barren land. This is largely because the efficiency of photovoltaic systems in general decreases at higher temperatures, and farmland has been created in areas with moisture. The cooling effects of vapor pressure is an important factor in increasing panel efficiency. In some cases, crop yield also increases due to the shade of the solar panels mitigating some of the stress on plants caused by high temperatures and UV damage. The term for this technique is called agrivoltaics and was originally conceived in 1981 by Adolf Goitzberger and Armin Zastrov, while it was coined in 2011. The mixing of big economical sectors with solar generation isn't something restricted only to agriculture. Take transportation as an example. Many companies are now working on solar-powered vehicles like solar automobiles, trains and buses, watercraft like yachts, and even small aircraft. An American company called Solar Roadways, on the other hand, is focusing on what is around the vehicles: roads. Their aim is to develop solar-powered road panels to form smart highways. If we decide to look deep into the urban environment instead, we're also going to find similar innovations of the type like solar trees. A technology led by Spotlight and Envision Solar, these trees capture sunlight and use it to power city infrastructure such as street lamps. Some of them might even have the autonomy to follow the sun as it moves across the sky during the day. Having distributed solar generation throughout a city leads to another interesting idea: solar charging stations for shared electric scooter platforms. A person gets rewarded if he or she leaves a scooter or any electric micromobility device in one of these little stations. Such stations might also work for charging drones used for micro-delivery, such as delivering small packages, ordered food, or medical supplies. You would also be able to charge your phone from these stations, although you might not need to, because as far back as 2009, we've seen solar phones, and with recent advancements in PV cells, many electronic devices might incorporate solar generation in the future. For now, the more promising ones are portable solar chargers, along with things like speakers and smartwatches. With the increasing globalization, all electronic devices, solar-powered or not, will connect into a giant network. A network whose communication is established by satellite technology. Satellites which are powered by, guess what? The sun. Sunlight is brighter outside the atmosphere and can shine almost all day, so space-based solar power has not only immense applications for communication, but also for powering spacecraft and space stations, along with space farms, which can concentrate the collected energy into Earth farms through a laser. In the future, we may even see entire space cities in the form of solar-powered or neo-cylinders. At the end, however, our most ambitious goal might turn out to be covering the sun itself with some type of solar conversion technology in order to form a so-called Dyson sphere, capturing most, if not all, of the available energy in our solar system.